value theorem?
It is.
I feel like we did this.
It is.
Didn't we do this in pre-calc?
No, you would not have. You would not have. Positive.
Then how did I know what MVT stood for?
I don't know. Did you call it? What'd you call it? What did you call it? Oh, not the. It's not the median. No.
What is it? Is it mean?
Mean. Mean. Close.
That sounds better.
Close.
So I also knew that. So
Sort of. Kind of knew it. Kind of knew it. Sure. All right, guys. Here's what we got. Okay. No, it's just it's with the it's just the draft with the hot cold. All right. Here's what we got. I'm going to share with you guys Rolle's theorem, and then Rolle's theorem is going to wind up transforming into the mean value theorem. This mean value theorem is one of the absolute most important concepts of the year. Okay, and it all hinges on Rolle. Okay, so here's what Rolle's theorem says. Okay, super important. I have three conditions that have to be met in order for Rolle's theorem to apply. Condition number one, I have to have a continuous function on a closed interval a to b. So would you guys agree that all four of these meet that condition? Yeah. They're continuous functions, closed interval, so endpoints are closed, right? Starting at A and ending at B. Everybody good with that? Okay. Condition number two, the function must be differentiable on the interval. Well, any sharp points? No, right? And that would be the only thing that would lead it to be not differentiable, because if it's continuous, we don't have any holes or any asymptotes, right? Or a curve like this. It could be a trig curve. Yeah. And then the third condition, guys, is that the endpoints have to be in the same y position. So do you see how these are in the same y position? Same height, in other words? Same height, same height, same height. If those three conditions are met, then Rolle said there has to be at least one point between A and B where the tangent line is horizontal.
Because basically it's like the exact same thing.
It's very similar. It's a very similar idea. I knew what he meant, but yeah, he actually.
We did that earlier.
Yes, we did. So what would be the slope? That was pretty good, Mike. So this is like the easiest way to go from 2 points A and B that are at the same y position, right? But what's the slope of this? 0. This would be one way I could do it. And what's the slope up here? I could do up and down, or any number of up and downs in there, creating a bunch of horizontal tangents, or I could go down and create this, right? So Rolle's theorem, he didn't really say anything that was all that crazy. He did some proof, right? And we're not going to do any of that, but he proved this, and in fact, it makes sense.
That's what I just said.
We'll get there eventually. Yeah, we'll get there eventually. We'll get there eventually. So, yeah, right? Yeah, exactly. So here's what I give you. I give you guys a function. I give you a closed interval. I want to know if Rolle's theorem applies, followed by any value where the horizontal tangents exist, right? So we got to know if it applies. First of all, is f of x a continuous function? Yeah, it's just a power function, right? Do I have a closed interval? Okay, so the third condition has to be that f of -2, come on, pen, and f of +2 give me the same value, right? That's what we got to figure out. Are they in the same y position? So -2 to the 4th. What is that? 16 minus 8. And this also gives me 8, right? So would you guys be comfortable saying that Rolle's theorem applies, right? And what I could say is what? Since f of x is continuous on the closed interval -2 to 2, and f of -2 is equal to f of +2. So what does that mean? That means at the endpoints, I'm at the same y position. Rolle's theorem applies. And f prime of x must equal 0 at least once on the open interval -2 to 2. So that's really important, guys, what I just said, that last piece. And what was that last piece? That Rolle's theorem suggests that there has to be at least one point between -2 and 2, but not including them, okay? So let's see if it makes sense. Let's take our derivative. And Rolle suggests that I can set this equal to 0. And I factor it into this, right? Which means that at 0 and positive and -1, right, I'm going to have horizontal tangents. One thing that's pretty important, guys, is what? I got to make sure that all three of these exist where? In the given interval, right? And they do, so yeah, we're good. That okay?
You don't have to put that like interesting.
What do you mean, in this you're saying?
Yeah.
Yeah, I mean, if I could, after doing this, I could say at least, I could say the Rolle's theorem applies and the derivative equals 0 at x equals 0 and positive and -1. I mean, I could do that if I wanted to, but the open interval. Exactly, and we're going to see that in a little bit. Okay, good? And so here's the thing, right? Rolle's theorem seems great, but it's kind of limiting, isn't it? What's limiting about it? What's the thing that makes it? They have to have the same y value, right? And more often than not, when I have a closed interval, they're probably not going to have the same y value, are they? Okay, they're probably going to have differing y values. And this French mathematician then loosened up the qualifications, right? So he did a bunch of proof and decided that, okay, well, this is great, but let's go a step further. And he said, what I'm going to do is this. I'm going to take those two endpoints, and I'm now going to not allow them to be in the same y position. So this one's higher than this one, right? And here's what the French mathematician came up with. He said, if I was to find the slope between this point and this point, then there has to be at least one tangent to the curve.
I was thinking about that.
That's, oh my God. Okay, so there has to be at least one point on this curve where the tangent is parallel to that secant that connects the endpoints. Exactly. Okay. It is a part of it. Yeah, this is going to bring us to a whole bunch of spots. Yeah, extremely important, right? So again, I want to make sure it's clear. You see how this endpoint's higher than this endpoint? That's why it's not Rolle's theorem, okay? And what do I have? I have a slope between these 2 points, and how am I going to find that slope? Using a traditional slope formula, right? And what I'm saying is on the curve that connects them, there has to be at least one tangent that's parallel to that secant. Okay? Right? And that's all the mean value theorem says. So, does it apply? Well, for it to apply, I've loosened the restrictions. I just have to be continuous and on a closed interval, and I have to what? Be differentiable on the open interval. Okay, as long as I have those two things, I'm good to go. So, is this a continuous function? Is it a closed interval? Yeah, is there any reason for this to have any points which are not differentiable? No, right? So, here's what I want to do. I want to know what is the slope between 0 and 2 on this curve, right? Now, do I know exactly what this curve looks like? Well, of course not, but we can get some values. 2 cubed minus 2 is 6, right? So if I did a really, really quick sketch, I have those two things that are happening, right? Those are the endpoints. Do I really know about the behavior between those points? I mean, could I graph it and all that? Sure. But do I really know what it looks like right now? I could figure it out, but we don't, right? So again, I want to make sure this is clear. I can connect these points, right? Maybe it looks like that. Or maybe it looks like that, right? Regardless of what it looks like, this is the theorem. The theorem says what, Eric? If I connect these two with a secant, then there has to be at least one point of tangency on this blue curve that's parallel. And would you agree that like over here, I have one right around here-ish? Fair to say? Yeah. So what am I going to do? I'm going to find the slope between these 2 points. And when I find that slope, it's going to be 6 minus 0 over 2 minus 0, which is 3. So what am I suggesting with this theorem? I'm suggesting that there is a tangent, right, somewhere between 0 and 2 that also has a slope of 3, right? So the mean value theorem suggests there must be at least one value on the closed interval 0 to 2 where the derivative equals 3. All right, so let's take our derivative. And what I'm saying is that there's got to be a value where it equals 3. Add 1, divide by 3. And I get the square root of positive and negative, or the positive and negative square root of 4/3. But the negative value of that does not fall within the given interval. So I have to reject the negative solution, and the only solution is the radical 4/3. Because it falls outside the interval, right? Cool? All right, this problem says we can use a calculator. With your help, with your calculator's help, let's figure this out. So, guys, this is one of those instances where I want to show you how you can use the calculator efficiently right? Because one of the tasks you're going to have is calculator section, and you're going to have to move quickly through it. And one of the ways that we can do that is using the define feature, right? And when I define a function, I can start moving quickly and do things quickly with it. So what I would do for this problem is I would define my function as x cubed plus 2x squared minus x. Okay, now what do I want to know about this function? Well, I want to know the slope of the secant that connects this point to this point, right? So what I'm really asking is this. If I were to add a page and graph this, okay, so there's my function, right? Now there are two endpoints. There's an endpoint at -1. There's an endpoint at 2. And I'm going to zoom out a little bit. Oh, don't do that. No, that's too much. No, zoom in. That's too much. Undo. All right. So what I'm suggesting, again, I want to make sure it's clear, guys, is between these 2 points, I can connect them, right, with a secant. So let's do that. Connect them. Points and lines. There's a secant between those 2 points, right? Now, what does the theorem suggest? It suggests that there has to be a point between these that has a tangent that is parallel to this one, right? Well, what's the slope of this? Oh, geez. Well, the calculator lets me do that too, right? Measure the slope. Slope is 4, right? So what I'm suggesting is that there is a point where the derivative on this curve equals 4. And I get that. And it's a squared, it's a quadratic, so I got to move the 4 over. (3x squared plus 4x minus 5, right? Now, what do I want to know? I want to know the roots of this, right? Okay, well, we got our calculator. Let's take advantage of that. Let's go to PolyTools. 3, 4, -5. So these are my 2 solutions, okay? Let me take a snapshot of those. All right, got my 2 solutions. What's wrong with one of them? Outside of the what? Outside of the interval. So we're going to get rid of this one. This one's no good. Hey, why did I keep, look at this? Huh? What do you mean it can't right over top of the picture? I just did.
It can't,
Except
because
right
the
there.
picture's set in the program to go over everything. That might change that.
Oh.
Well, now we can't see it because that has its own boundaries. You just move this into like a page or something.
Oh, whatever. Okay, so
Screenshot.
let's get rid of this one. So 0.7863, right, is where that should happen. Now check it out. Let's go back here. Let's go to 0.7, what was it? 683. That's going to bring me right, oh, close enough. That's going to bring me right here, right? And remember that we have the ability to ask the calculator for a value of a tangent at a point by simply going to analyze calculus dy dx. So I want to know what is the slope at this point, and it's a little bit off because I put in the wrong number. What should it be? It should be 4. What was that number again? 7.7863. And when I change it, that also changes to be 4. Okay? So there you see a perfect visual of the theorem, right? And it makes sense, doesn't it? I mean, it would be crazy to think that it doesn't happen, right? So it has to happen. And there you see it. So Weeks asked a good question earlier. She said, Picardo, if I'm actually at that endpoint, do I have to reject it? Yes, because what does the mean value theorem say? It has to happen, the derivative has to happen in the open interval, absolutely, right? So with this problem right here, if I use the mean value theorem, 27 minus 27 plus 6, I think it's 6. It is. All right, so does it apply? Well, it's continuous. Yep, it's closed, so it looks good. If I were to take this slope, it's going to be 0 minus 6 over 0 minus 3 gives me a slope of 2. So there better be a point on the derivative that has the same slope as the secant, right? So the derivative is this. And I know that the derivative by the mean value theorem better equal 2 at least once. And I get x equals 0 and x equals 2. And this is where Weeks says we have to get rid of that 0, because that 0 can't happen. Right, Michael?
I mean, I agree with the math, but I'm kind of salty because I didn't, for the rest of these, I solved all of them before everyone else, but you guys solved this one before I did because I didn't have this paper. I didn't want to,
It's okay.
but I solved it just after you guys did. But you're right.
Well, thank you. I was pretty sure. You're right that I'm right. Yeah, we're not going to talk about this. I stole some of it. Some of it's other work. Yeah. No, some of them, not most of them.
Did
No.
you rewrite them to add more jokes? I would do that.
I know. Well, how dorky, right?
That would make a jack-o'-lantern jealous.
Probably, yeah. Yeah. I kind
I
of am.
arrested someone for integrally being a part of a series to derive.
Michael, what's wrong with not you, but this? What's wrong with this function? Why does the mean value theorem not apply?
It's not continuous.
Where?
It's not continuous at all.
So here's the important thing, right? I don't want you to say, Michael, I don't want you to say that it doesn't apply because it's not continuous. What I want you to say, it's not going to apply because it's not continuous at a point that lies within the interval, right? So in other words, irrelevant. Irrelevant. Yeah, exactly. So had I changed this question, well, no, where's the discontinuity occur? 1. So if I have any interval that doesn't contain 1, it works. Yeah, it works, right? So the only time it's not going to apply is when the discontinuity occurs within the interval, right? So since f of x is not continuous at x equals 1, which is an element of that interval, then the mean value theorem does not apply. On the interval -3 to 5. The mean value theorem applies somewhere else. Precisely. Yep. And this next one, guys, is our first introduction into a concept that I want you guys to always keep in mind. Anytime we have something to a fractional exponent, now remember that x to the 2/3 would be the same as this, right? So it's not just fractional exponents, it's also radicals with different roots and bases and things like that, right? Anytime you see this, what often is going to happen, guys, are cusps, okay? This right here is going to create a cusp. Now, here's the thing that you're going to worry about. Hang on a minute, Ricardo. I know there's a cusp. I know at cusps, I'm not what? Differentiable, but it might not be in the interval, right? So what I need to do is, first of all, why is there a cusp? Well, if I take a derivative of this, I get 2/3 x to the -1/3, right? Which is the same as this. And what do I know about this derivative? Where does this derivative not exist? At 0. If the derivative doesn't exist at 0, then is this differentiable everywhere between -3 and 3? No, right? And so this does not have the mean value theorem applied because it's not differentiable everywhere between -3 and 3. Now, if you were to look at what this graph is, it's x to the 2/3. And there's your graph, right? And we see that that cusp happens at 0, right? And so since it's not differentiable there, it's not going to have a mean value theorem that applies. Cool? That's a good question. Sometimes, if it's just something like this, then probably. But I mean, more often than not, there'll be, there'll be like a 5 here, and then minus a, I don't know, a sign of, you know what I mean. You're gonna get something like this. But regardless, what happens? Right? I mean, so it's still at 0. Yeah, it's still at 0. But again, there are other things that I could do, right, with that. Yeah, isn't that? Look at that. Looks like some kind of like.
That's